Hello, my name is Tejas and I am from VIT Chennai, and my topic name is Diffie-Hellman Key Exchange Algorithm. So this topic is a part of my digital assignment of course Blockchain and Cryptocurrency Technologies. So before going to Diffie-Hellman Key Exchange Algorithm, let's see what we are going to discuss in this video. So first we will discuss the problem statement. So basically why we would need the Diffie-Hellman Key Exchange Algorithm and where do we need it. Then second we will see the introduction, like we will see some basic details about the Diffie-Hellman key exchange algorithm, and then we will see one-way functions working. So here we will see a simple example which will help us to understand more about the Diffie-Hellman key exchange algorithm. The next is steps in the key exchange algorithm, basically what are all the steps involved, and after that the practical implementation. So basically it will involve one example of how Diffie-Hellman key exchange algorithm works, and finally we will see the applications of it. So coming to the problem statement, now a significant portion of the today's internet is encrypted using secret encryption keys. So basically whatever message we want to send to some person or during any transmission of data, like today's most of the things or the data has to be encrypted, and encrypting communication channels maintains both the confidentiality and the integrity of the data being transmitted. And the exchange of these secret keys had always been a challenging task until the development of the Diffie-Hellman key exchange algorithm for public use. So for encryption, for encrypting the data, first the users have to send the some secret sharing key so that they can encrypt the data and decrypt on the other side. But if this secret key is shared on the common channel, then anyone hacker or any interceptor can hack the key and he can decrypt all the messages and can intercept it. So basically Diffie-Hellman key exchange was developed for this, and it really helps to solve the problem. It also helps to solve the problem of exchanging symmetric encryption keys without compromising data integrity. So let us see one example why we would really need the Diffie-Hellman key exchange algorithm. So consider Steve and Emma are two persons, and Steve wants to transfer data to Emma with the encrypted data. So before transmitting the encrypted data, he has to share a secret key to the Emma. Now if he wants to share the secret key to Emma, there are the chances that while sharing on the public line, there may be some hacker or some interceptor tapped at the line, and he may intercept all the messages and all the secrets that are shared to the Emma. So if Steve shares his secret key through the public line, he can easily intercept the message, intercept the secret key, and this will lead to compromisation of data, or he can decrypt all the data from the Steve to Emma. So basically let's see about the Diffie-Hellman key exchange algorithm. So this algorithm securely helps to exchange keys, and it was proposed in 1976 by Whitfield Diffie and Martin Hellman. So hence its name is Diffie-Hellman, and it's communicated over insecure channels. So basically as we seen, like while transmitting data from insecure channel, we use this Diffie-Hellman key exchange algorithm, and it is also used as a precursor to asymmetric cryptographic algorithm. Now to understand the Diffie-Hellman key exchange algorithm, we will see how one-way functioning works using a simple color exchange algorithm. So this will really help to understand the Diffie-Hellman key exchange algorithm. So let us assume Steve and Emma again. Now what they have to do is they have to select a private color of their own. So assume Steve selects red as a private color and Emma selects the blue as a private color. Then both of them have to decide on one common public color. So let us assume they decide yellow as a common public color. They decide this over the public channel, so even hacker or interceptor can have the access to this color. Now what the Steve does is Steve mixes his red color with the yellow color, that is the public color, and it gets a mixed color, so we get orange color. Now similarly Emma also does the same, so she mixes her blue color with the yellow color and she gets the green color. Now both of this mixed color will be exchanged between them. So this will while exchanging, there is a chance that hacker is seeing this and he can get both the colors. So now Steve exchanges the color and similarly Emma exchanges the color. and here we can see the hacker, whoever is, he will get both the colors. Now what will Shiv do? Whatever color he obtained from the Emma, he will add his private color to the obtained color, and similarly Emma will do the same. So what happens, he adds a color to green color to red color to the green color, and similarly Emma adds her blue color to the orange color. Now we can see both of them finally gets the same color. So basically at the final stage, both of them able to get a same secret color, and without knowing the hacker know. So whatever combinations he tries with the orange, yellow or this green color, he won't be able to crack this common secret color between the Shiv and Emma. So basically this is a simple example of how Diffie-Hellman algorithm would work, but the Diffie-Hellman algorithm would work on numbers. So as it is related to cryptography, it works on the modular mathematics. Now let's see the working of Diffie-Hellman algorithm. So it involves three basic steps. So the first step is assuming a prime number and selecting its primitive root. So let us assume a prime number to be q, and we have to select alpha as a primitive root of q. So what is a primitive root of a number or primitive root of q? So alpha is said to be primitive root of q if and only if it satisfies the following properties. So if we take alpha mod q and alpha squared mod q and alpha cube mod q until alpha raised to power q minus 1 mod q. So whatever values of this would range from number 1 to q minus 1, then only we said that alpha is a primitive root of q. So this is a condition required for the primitive root. Now after finding the alpha and q, they will decide the alpha and q commonly between the Shiv and Emma. After that, what they have to do is finding the private key and public key of the sender and receiver. So basically now Shiv will assume a private key. So let us assume xa as a private key, and xa has to be smaller than q. Now in order to calculate his public key, that is if we relate with the previous example, that is a mixed color. So this public key, that is ya, is calculated using the following formula, that is y is equal to alpha raised to power xa mod q. And in this way the Shiv will get two of the keys, that is one is private key and one is a public key, that is the xa and ya. Similarly, Emma will also assume a private key and find a public key. So she would assume, let us suppose she assumes xb as a private key, and xb also has to be smaller than q, and she calculates the yb, that is a public key of Emma, using this formula, that is alpha raised to power xb mod q. And after this she also gets her own private key and a public key. Now what happens, the Shiv will exchange his public key, that is y, to Emma, and similarly Emma will exchange her public key, that is yb, to the Shiv. So after exchanging, like they would have Shiv would have xa, yb and q, and Emma would have xb, ya and q. So after this they have to generate the secret key at the sender and receiver side. So both of them will generate the secret key with the obtained information. Now to generate the secret key, what they will do is use this formula, that is k equal to yb raised to power xa mod q, and similarly Emma will do the same, the obtained key, public key raised to power her own private key raised mod q. So this would generate a same common key named k, and with this information, the yb and ya, no matter how hacker would try, it would take eons of years to crack the secret key that is shared between the Shiv and Emma. So now why this happens, if we see that yb is calculated using xa, alpha raised to power xa, and alpha raised to power xp, and this raised to power xa mod q will give the k. And similarly y is calculated as alpha raised to power xa and this raised to power xp mod q. So basically due to this they will always generate a same common key, that is the k, using this formula. Okay, now let us see the practical implementation of this. So as a first step, we will assume a prime number. Let us assume q as 17, and we will select a primitive root of q. So let us assume alpha as 3, that is a primitive root of 3. So let us check whether the 3 is primitive root of 17 or not. So if we do 3 mod 17, we get 3, 3 squared mod 17, 9, 3 cube mod 17, 10, and similarly so on. If we do, we get 3 raised to power 16 mod 17, 1. So all of these values that we obtain after mod are lies between the range 1 to 17. So it is smaller than 17. Hence, we can say that 3 is a primitive root of 17. Now, both of them will decide their private key. Now, let us assume Shiv decides the private key as 15, that is XA as 15. And to calculate his public key, he will use a formula, that is y is equal to alpha raised to power private key mod 17. So 3 raised to power 15 mod 6, 17 gives us 6. And hence we obtain both the private and public key for the Shiv. Now 15 is the private key and 6 is the public key. Next is Emma will assume XB as 13, her own private key as 13, and she will find the YB using the same method. So after doing the same method, she gets the public key as 12. Now Emma has her private and public key pair as 13 and 12. Now both of them will exchange, so she will give 6 to Emma and Emma will give 12 to Shiv. Now after that, we get at the Shiv side, we get his private key, Emma's public key and Q, and at the Emma's side we get her private key, Shiv's public key and Q. So using the formula, K is equal to YB raised to power XA mod Q, we get 12 raised to power 15 mod 17, which is equal to 10. And similarly, Emma also applies this formula, that is 6 raised to power 13 mod 17 is equal to 10. And both of them, we can see they have generated a common secret, that is the 10 between them. Now this example we took really small numbers, but in the real life scenarios the numbers are really huge. So it would take decades or eons of years to calculate or try using trial and error method. So hence we can see how powerful this Diffie-Hellman key exchange algorithm is. Now let us see some of its applications. So it is used in public infrastructure, SSL TLS handshake. So basically SSL TLS is are the certificates that are used on the websites on the browser, and the secure shell access. Then secure shell access, like we have to access remotely some terminal using a third party application, then we can then for that also the Diffie-Hellman key exchange algorithm is used. Then another of the application that can be used is to implement a smart contract. So DHKE, that is a Diffie-Hellman key exchange algorithm, can be used to implement a smart contract, and it can be used to create a system which can communicate only via the Ethereum blockchain and provides both backend and client side code with the smart contract. So in the it can also be used in blockchain, and it has the following application. So DHK is really important for transferring of the secret key between the users. Thank you.